Hello! We will learn about waves now. Waves in a string. So this is lecture 1 or part 1, where we will derive the partial differential equation that govern waves in a string. Then there will be another lecture where we try to derive the finite difference scheme. Then in lecture number 3, we will do an actual implementation of the numerical solution on MATLAB. So we will develop a computer code to solve the partial differential equation that govern the waves in a string. Waves in string lecture series will be divided into 3 parts, which means there will be 3 videos, 1 video for each part. So in part 1, we will derive the partial differential equation that governs the waves in a string. And in part number 2, we will deal with the finite difference scheme. So we will develop the finite difference scheme. And in part number 3, we will deal with the numerical implementation. Okay, we will deal with the numerical implementation on MATLAB. Okay, so let's start part 1, which deals with derivation of the governing PDE of the waves in a string. So let's consider a string, and this string is vibrating, okay? And this is the axis that shows the length of the string, let's say from 0 until L. And here we have the vertical displacement of the string. So it's denoted by U. Now if we discretize this string into small pieces, then let's zoom only here and take that piece. So what we get something like this. So these are like pieces of the string. These are like pieces of the string. Okay, we take pieces of the string at different discretizations. Okay, so if this is x axis, this is y axis. We call the y axis here u for the vertical displacement, and in the x axis we have a uniform grid. So let's say this is xi, this will be xi minus 1, and this will be xi plus 1, and so on. Similarly, for the vertical displacement or the vertical position of the particle will be, for this mass, let's call this mass mi minus 1, and this piece has a mass of mi, and this piece has a mass of mi plus 1. So this has a vertical position ui minus 1, this has a position ui, and this will have a position ui plus 1. So to derive the equation for waves on string, we assume that the string is discretized into discrete point masses, okay, and with elastic strings in between each mass. So at point, for example, at point xi, we have mi, which is the mass, and this mass, or this point mass, moves vertically with a displacement ui. So ui is actually a displacement that is function of time. So it vibrates vertically with as a function of time. Good. Now there is a tensile force, of course, between the each mass, each point mass. So for example, we have here T and we have another T here. And this tensile force is constant, okay? Is constant and it is large, okay? It is constant and it is large. Good. We will use Newton's second law of motion. We'll use sum of the forces is equal to the mass times acceleration to derive the partial differential equation that governs the vertical movements of those point masses, okay? Now, let's see what we have. We have the mass mi here, which is located at position xi on the x-axis. And we have another mass here, which is mi minus 1, which is located at position xi minus 1, and another point mass here, which is mi plus 1, which is located at position xi plus 1. Now we will assume that the distance between each 2 point masses is fixed and is equal to delta x. The vertical displacement, we mean, for mi minus 1 we have ui minus 1, and for the point mass mi we have ui, and for the point mass mi plus 1 we have ui plus 1. I'm going to call this tensile force as T left, and the other tensile force between the mass mi and mi plus 1, let's call it T right. Okay? Then we will denote delta ui as the difference between ui and ui minus 1. Okay? So this vertical distance between mi and mi minus 1, we will call it delta ui. And we have also delta x is xi minus xi minus 1. So if we denote by theta this angle between the tensile force vector and the horizontal distance between the two masses mi minus 1 and mi, then we can calculate sine theta and cosine theta. Okay? So we will need the distance between mi and mi minus 1, and let's call this distance as delta si. In this case, sine theta will be equal to delta x divided by delta si, and cosine theta will be equal to delta ui divided by delta si. And the position of the mass mi at time t, so will be xi times I plus ui at time t times j. So I and j, these are what? The unit vectors, okay? These are the unit vectors. Good. Now we will decompose the left tensile force T into component on the x-axis and another component on the y-axis or the vertical displacement axis. So it will be equal to, good. Now if we substitute sine theta equals delta x over delta si here, and doing the same for cosine theta, then we can achieve at this. Similarly, for the tensile force on the right side, Tr, between the point mass mi and the next point mass mi plus 1, it will have two components, one positive component on the x side, which is t sine theta, and another component on the y-axis which is a negative one, and it is equal to t cosine theta. So tr will be equal. Now if you recall, sine theta is delta x over delta si, and cosine theta is delta ui over delta si. So we will have t on the right side will be equal to, now delta si is equal to delta ui squared plus delta x squared, and delta si plus 1 in a similar manner will be delta ui plus 1 squared plus delta x squared under the square root. So to summarize, we have developed the equations for the tensile force on the left side and the tensile force on the right side. So we decompose them into components on the x and y axis. We have also these helpful equations for the difference in the vertical displacement between two consecutive point masses, and this is the last one. But we have to be careful here. Notice that for delta ui, what we have, it is the difference between ui and ui minus 1, but it is written as ui minus 1. However, delta ui plus 1 is ui minus ui plus 1. So please pay attention to this, okay? So later we don't get tripped with the signs, okay? So let's set up now the equation of motion using Newton's second law. So remember, we have these three masses, point masses, mi minus 1, mi and mi plus 1. So the only force that is applied is the force on the left, the tensile force on the left, and the tensile force on the right side of the mass mi. Now, so we know that the Newton's second law states sum of the forces is equal to the mass times the acceleration. So the force that we have the force on the left, tensile force on the left, plus the tensile force on the right shall be equal to the mass times the acceleration, and it is u double dot I t times g. Okay, now on the x-axis, it is not important to write the equation of motion since it will just lead to tensile force is equal to the tensile force. So we will just discard this, and we will focus on the sum of the forces in the vertical direction. So in this direction, what we have is the following. So we have only the components on the y-axis. So we only take these two components. So we'll have SI as be equal to the mass times the acceleration at time. So this is the most important component of the equation of motion. Good. Now we will assume two things. First, very small displacements, and very small displacement gradients. We mean here by displacement gradients is delta u I over delta x. Okay? So assuming very small displacements, and we have delta si is equal to the square root of delta ui squared plus delta x squared. Now if you put delta x outside of the square root, you get this. So you get delta x times delta ui squared over delta x squared plus 1. Now when we assume small displacements and small displacement gradients, this term will tend to go to 0. So we will end up with delta x square root of 0 plus 1, which is delta x. So what we get is delta Si is approximately delta x. Now we can go back to this equation and replace delta Si in these two terms by delta x. Then we divide the whole equation, both sides of the equation, the left and right side of the equation, with delta x. So let's do just that. So this is the equation motion in the y-axis. So as we said, delta Si will be replaced by delta x, and we have also delta ui is equal to ui minus 1, and delta ui plus 1 is ui minus ui plus 1. So we have minus t delta ui over delta x minus t delta ui plus 1 over delta x is equal to the mass times the acceleration. Now let's divide by delta x, and you will see later why we do that. So we'll get minus t, or we can just put here t over delta x squared times delta ui negative delta ui plus 1 is equal to the mass over delta x times the acceleration time t. Good. Now what we do here, we replace this by what? By rho. Rho is the density. Rho I is the density. Okay? Density at point mass I. Here, remember, this is just point mass I. So I have substituted mi over delta x with rho I, and now I wanted to expand minus delta ui minus delta ui plus 1. Now recall that we have from the previous slides, delta ui is the difference between ui and ui minus 1, but we have here the negative sign, so we will get here ui minus 1 plus minus ui. Then we have negative delta ui plus 1, so we will get plus ui plus 1 minus ui. Good? Let me just put this together. Then if we simplify this piece of the equation, we get ui plus 1 minus 2ui plus ui minus 1. And we have here over delta x squared. So if you put this over delta x squared, this reminds you of what? When delta x goes to 0, this will be approximately second derivative of u with respect to x. Good? Now let's substitute this term with the second derivative. So we get t times, I'm going to use uxx to designate the second derivative of the vertical displacement, with respect to x is equal to rho. I'm going to also to substitute rho I with rho at x, okay, or simply rho. And the second derivative here is with respect to time, here the acceleration, so it is just the utt. So we get rho utt. So if you divide by rho, what you get, and rearrange the equation, you get utt is equal to t over rho times uxx, or utt is equal to c squared times uxx, with c squared is equal to, or c, simply, c will be the square root of the tensile force divided by the density. Now, this is called the wave equation, okay? The wave equation. And c is the velocity or the speed of the wave. And this concludes this part of the lecture. In the next part of the video series, we will derive or set up a finite difference approximation scheme. And in the third part of the video series, we will implement the finite difference solution scheme into a computer program on MATLAB.